Day two, we're going to be talking about smart infrastructure and with a bit of focus on smart grids. The lecture today in the morning, the lecture is brief. I only have around 30 slides. Most of it is going to be activities. So today you're going to get an idea of basically the whole course. Is going to put things in perspective. You're going to understand how cloud computing fits in the picture, how smart transportation and other smart infrastructure relate together. Okay, so when we talk about smart, what do we mean by smart? What defines smart? This is a word that is being used far too often these days to sell stuff. Smart TV, smartphone, smart, yeah. So what does it mean?
Like, it contains artificial intelligence, so...
Contains artificial intelligence. Wow.
Like things. So
what is artificial intelligence?
So just like it has a processor, so...
Okay, so artificial intelligence is a field in computer science whereby you make machines learn and do some type of, I guess, optimization based on that. And you have different fields in artificial intelligence. You have neural networks, you have reinforcement learning, and one other one I forgot. And machine learning. So that's one type of intelligence that you can have in a machine. But let's try to figure it out from a systems perspective, from an engineering perspective. Okay? When we say smart, what are you doing? Yeah.
A smart device is a device that does more than what we expect it to do. For example, a smartphone, it's used for calling, but smartphones nowadays, they run apps, they have cameras. Same thing with smart TVs, they're running apps as well. So
okay. So when we say intelligent, what is the intelligence on? What is it using to become intelligent? You mentioned cameras. You mentioned other things within the device. Sensors. Software. Okay. So how do those relate? If you make a new product, are you allowed to call it smart? Why not? Is there a standard? Is there a standard?
You just make a new product, it's just a product.
Okay, let's start dissecting this. So we want to know what is the smart in smart infrastructure. Okay, and that includes also the smart devices. One way of defining smart infrastructure is the following. This is our view of smart infrastructure. It is one that adjusts to changes that are happening around it, and it uses that to have optimized performance over time. Okay, so remember yesterday we were talking about variations, about agility, about varying demand. That's a type of change that you have, right? And being able to optimize the performance of your system, of the systems also that you have, that you're running over time, is what makes something smart. Okay? For example, yesterday Billy was telling me about how his laptop has a feature where if it detects that it's in free fall, so it's falling, the hard drives turn themselves off. That's something smart.
The needle retracts.
So isn't that something smart? Like, I find it to be something, because it's detecting, it's using some type of sensors, right? And it stops turning the hard drive so that at least you don't lose any data due to the fall. So that is improving the performance, at least. We're going to go to different examples of these. I just remembered that now. So to start with a smart infrastructure, what is the raw material? What are you starting with? For a car, you need different types of, I don't know, metals, wheels, fuel to run. For smart infrastructure, what do you need? You have the infrastructure. You have, I don't know, a bridge. You have a sensors. Why sensors?
You're adjusting to changes in your environment. So
What you were going to say?
They're
They're the inputs. So the smartness is in the additional information that we're getting. Okay? So you get data from sensors. So when a device has sensors, if you take into account like the smartphones, if you take into account some of the fridges that are called smart now have additional sensors into them. Okay? If, let's see, for example, the the digital cameras that are detecting someone's face when you're taking a picture, that's a sensor, right? That sensor and also software. So this information that you get from the sensors, this data, this has to flow back to a system. So you need a communication system that helps this data flow to the system. That's the second component that is important, that is required. Next, you need a central system that takes this information and does some type of optimization. So based on this information, based on possible information from different sets of sensors, it improves the performance of the system. Now, this information sometimes has to go back and be implemented, especially if you're a central system in charge of several different components. So this central system might need to send the resulting decision, how you're going to improve the performance, to a controller. And we'll go into examples of these. And finally, this controller will need to make this new action for optimal performance. I think it's coming up. One simple example is you're crossing from the Bayhan Center to Galbraith, and you press the pedestrian crossing button. So after you press that, there's a sensor that detects it. You have an optimization that happens based on that, the green light cycle of the north-south direction on St. George gets shortened, so that, and then the result goes to the controller, which changes the traffic light, and then you can cross. Okay? That optimizes that optimizes the performance so that you can actually cross the street, or else you'll be waiting there and you'll be coming in late. So let's see. Smart infrastructure example. Yeah, so this is what I mentioned. Advanced traffic light on an intersection. Here you have sensors from all of the on all the approaches. So a direction in which vehicles or people might be coming are called approaches. So one of the things that that is required, let's see if you know this. If you have a major road such as, let's say, St. George, and then you have a smaller street like Harvard, a bit north of here, how do you decide which direction has a longer cycle? So how long the vehicles would be going in one direction, then you stop it, that gets a red light, and the other direction, yeah.
So like that, like where I live is like Station Minor Road. So like what they did was like they have like a sensor in the road. So like if it detects that there's no car there and no one has pushed the pedestrian button, it will extend the time on like the major
Yeah.
road.
Okay. What are
Sensors and magnetic field.
okay?
I read it somewhere, like basically like on the side of the road, you sometimes see like the bumps like this high, this big.
Yeah.
And, like,
We're going to discuss this. Yeah.
Oh, I was gonna say based on the volume of the number of cars on each road, you can tell which one needs to fix.
Perfect. So all these are correct. So you start with what Kartik is mentioning, so which is based on the volume. So you'll be measuring. You have devices at the in the pavement, Solomon. You have devices in the pavement that are inductors that they detect how many when a vehicle goes through. Okay, that those are called loop detectors. We're going to discuss them in detail tomorrow. That's how you can measure how many vehicles are going through on the different approaches. You use that in order to create pre-timed cycles. So if you don't have if you don't have pedestrian lights, if you don't have additional things that you're detecting, you'll have set times. So let's say 40 seconds for this cycle, then the opposite, let's say the east-west one would be 25 seconds if the north-south one has a higher volume, right? Because you want to optimize based on that. And then in addition to that, if you have at night, usually those pre-timed signals get changed into actuated and fully actuated, which means that depends on additional sensors. So when you have no vehicles coming on a small approach, then the north-south one, for example, would always have a green light. Unless one vehicle comes, that gets detected, and then the traffic light switches after a few seconds. If you want to know about these further, we covered these in the deep course last year. So it's day 5. If you go through the website, it's in the recorded there, and the students are actually presenting this material. Okay. So going back to smart infrastructure, we said that this needs several sensors. Sensors in the pavement, sensors that pedestrians will be pressing. And the data from all of these sensors, as you can notice now, you don't have one item, right? You have from different places. They have to go into one place to have a decision. And so all of these need to coordinate together, right? You can't have this traffic light decide, oh, I'm going to give it a green, and this one do the same. What are you going to have? A crash. So these have to work together. So these sensors will need to send data to a central system through a wired or sometimes wireless system. Then you have optimization that happens for this using this data, and the cycles, how long the green cycles on each approach gets decided based on this data, and also, as I said, depending on the time of the day. And after that gets decided, it could be, let's say, in this box, okay, the big box sitting at the side of the street, and then that goes back to each of those controllers, which are embedded in the traffic lights, and that will be updating the cycle for optimal performance. Okay, so these are the elements that define a smart infrastructure. This is another one. This is again from transportation, advanced parking indicator. So this is, I took this last year in downtown Montreal. For people who can't see there, this is showing how many parking spots are available in the city in different parts of the city. So Vieux Montréal, Palais de Congrès is 334, and Centre Commerce is 99. So those are the empty spots available in those different areas. Okay, so this is on like a main road. So before you go and attempt to find parking in those spots, you know ahead of time. If you see 5 here, then you'll be like, I'm not going to go there. Let me go somewhere else to park. Okay, now let's try to identify from a smart infrastructure perspective, what are the components that are required to have this enabled? And I hope they have stuff like this in Toronto soon. Toronto is bigger, so doing stuff like this usually takes more time. So what do we need? Yeah, money. Of course we need money. Yeah.
You obviously need the sensors.
Okay, where do we need the sensors?
Underneath the parking spot.
So
each
every
and
single parking spot, you would need a sensor that tells you whether there is someone there or there isn't someone parked there. Yeah.
Couldn't you like technically sort of cheat a bit and put one at the entrance, one at the exit, and then see how many cars?
Yes, you can, and that would be using image processing, specifically video processing. So cameras, through cameras, you'll be trying to detect basically a queue of vehicles that are parked. But that's also expensive. You would need that at several different places. Yeah.
Can't you just put one at the toll thing where you pay for the parking spot?
One at the toll, if you're assuming that you have a parking like garages with entrances with a toll, yes, you can do that. However, this, I think, includes also street parking. This isn't just, these are for different areas where like you have residential areas and businesses. It's not just, let's say, a floor of parking in a mall. For that, you can just put one at the entrance, definitely. One of the small issues with a system like this is if someone has parked in a wrong way, then the sensor will not detect it. I saw this in Dubai a month ago. So we're going around looking for a spot, and both sensors tell you that there are two sensors next to each other that are green that says you can park there, but one person has actually parked sideways on the two spots. So you have to account for situations like that when people don't know how to park. Okay, so we start with the sensors. You need it for every street parking spot. Then that information needs to go to a central system. Now, the central system, it's not trying to solve a problem here. It's just displaying it. Okay? Now, how is that display of this information optimizing the performance of the system? In terms of performance, what are we interested in? Why are we doing this? Why are people spending money to do this? So you don't waste time, so reducing delay. Yeah.
Less traffic on the road?
Less traffic, especially parking traffic delays a lot of people. Okay? So reducing some congestion. Did you have anything else? Okay, so now that's the goal. How are we reaching that goal? Remember, we said you have information flow, communication system, central system, you have some type of decision being made. Who's making that decision now? Who's making the action based on this data? Computers? No. Yeah. Us. So the person who sees this display is the person doing the optimization. They are doing the action, okay? And that action is reducing, let's say, the congestion in this area, and it's reducing the delays. You don't go somewhere when there's no parking, or else you just turn around and you will just delay other people, especially the ones who are just trying to use the road. They're not parking. So drivers change their routes to increase their chances of finding parking spots. Okay? And it also reduces delay. So that's where the optimizing the performance is happening. Okay. This is, okay, we've talked about smart infrastructure. Now let's think about cloud computing. Okay, so we talked about cloud computing yesterday. Try to think of it from this perspective. How can you find these 5 different components? Where are they? Yeah. What you?
Traffic control, like for example, you can have like 2 different tunnels.
No, we're talking about cloud computing. I'm not saying how you use cloud computing for this. I'm saying how is cloud computing a model of smart infrastructure? Yeah.
Because it optimizes resources depending on demand.
It optimizes resources based on demand. What are the sensors? What are you sensing? What is the data that you're getting? One of you. Yeah. You. Remember we were talking about the Boxing Day sale? What's the data there? What is your input? The transactions, right? So the demand that you have. You have an idea of the demand, but it's changing in real time. Okay? So you sense the demand. You know how many people are wanting to buy stuff. Okay, so that's the data. And that goes to some central system through what mechanism? What's the communication medium here? Usually the internet, right? For cloud computing, it's usually the internet. In then where is the optimization happening? What does the central system decide? What is the action that it might make? Yeah.
It'll change the amount of allocated resources.
It will change the amount of allocated resources, or actually, unless it has a private cloud, if it's using a public cloud, it will request changes to the amount of resources. So if the demand is going up, it will request more resources. It will request more storage, more computing. Okay? If the demand is going down, it will reduce those. And also, it could be a request for networking. And the decision or the actual action which is being made and would then be providing those resources to meet that demand. Okay? So this is how cloud computing is also a model of a smart infrastructure. And in a bit, we'll see how cloud computing is an enabler of smart infrastructure. So a different point of view. OK, so now let's try to look at it from an ICT perspective. So information and communication technology. How did we arrive to this notion? How did we have this type of smart infrastructure? We started with a lot of old telephones. Has any of you used a phone like that? Raise your hands. OK. Willingly or just who has it done willingly? No, not just for fun. That's the phone that you had. OK, some of you. I've used that for several years. I'm a bit older than you guys. Before these came up, there were even bigger versions than these. So all of that technology changed. This is a picture of the internet. Okay, the darker blue ones are the concentration of servers in the internet. Okay, and you see you have different zones of very concentrated areas, and then it gets sparse when you move away. And these are modern day server rooms. Okay, so newer than the server room that you saw yesterday. Lots of things like this, lots of sensors on top of them, a lot of things being automated rather than go and physically remove stuff and then change things. Okay, and all of this technology is driving major socioeconomic change. Okay, we're talking about jobs yesterday. A lot of the jobs that existed do not exist anymore. There are lots of new jobs that need all of these technical skills, and it enhances the way that we do things, the way we interact, the way we teach, lots of things in everyday life. One of the other things is Moore's law. This is a concept from computer engineering, whereby the semiconductors, which are the components that go into every electronic device, are getting smaller and smaller. Okay, so you can actually put in far more semiconductors into the same space. It's the material silicon, and all chips, all electronic components are based on that. So that's why desktops, laptops, all electronic devices are getting smaller. Okay, you remember even like when you were young how big computers were, how big hard drives were, and how you can how you have smaller things. You have computers now in cell phones, right? So you have PCs are now available everywhere. Software and the languages and all of those are now far more common. A lot of people are now starting, even among you, learning programming at a far younger age. So internet was not common to every home when I was growing up. Now it's common. And Ethernet, you were saying Ethernet is not being used much anymore. It is, and a lot. And you have new computing models. So you don't even have to do the computations and the processing on your own device. You can do them through Google and Amazon and all of these different devices. You were talking about the Think clients yesterday from the video. And virtualization and any X as a service. So that is the software as a service, platform as a service, infrastructure as a service that we mentioned. So you're having all of these changes based on the major developments in technology. And here you find, again, the benefits of cloud computing for these. So pay-as-you-go utility, you don't have to have the initial cost. You have 5 times 7 reduction in cost. Dynamic movement of virtual machines. So based on the additional needs that you have, your virtualized resources could be moved from one place to another, and then you have additional resources coming from different locations. And you have a fast you have basically lots of demand for bandwidth. The internet speeds are getting higher and higher, which leads to fast growth of volume of carbon emissions. Okay, so that's one of the byproducts that is happening. Now, this is also this is a model of communication between devices. This is looking like a cloud. This is a technology developed by a research group in the EC department, and whereby you have all the different sensors in different places in industry, environmental, commercial, and they're all communicating together without internet. So it's replacing the internet layer with a different technology. So because of the massive growth of the sensors and this information. So this new technology whereby you have a growth of all of these devices, all of these sensors, is now leading to this new fields of smart power grids, screen computing, vehicles talking to each other, communications, and collaboration between the different sensors. And cloud computing is acting as the enabler for smart infrastructure, because it is providing the means and the mechanism for communication by virtualizing the resources that you have between these devices. Plus, after collecting all this data, doing the processing for it and optimizing based on that, because of the sheer scale of the data, you can't run it on a simple machine anymore. Okay? And depending on transactions, the demand that you have, you'll be using the cloud resources to run that data, to process that data and to optimize your performance on that data. And with the increase of carbon emissions that you're getting from all these technologies, it is having the smart infrastructure, having these intelligent decisions being made are important to reduce the emissions. So, for example, if you don't optimize how you're aggregating, filtering, and processing that data, and you're collecting all of it in one place in one city, and you're collecting it from everywhere in the world, that's a lot of cost, right? Plus, you're doing far additional things, and you're using far more resources than you need. What if you, based on your need in each area, you collect the data there, you rent resources there, okay? You go from a cloud service which is close to there, you optimize based on that, and then you go back, you implement your results. So let me give you an example. You're trying to identify the possible start of a fire in a forest, okay? And your forest is, I don't know, what's the biggest one? The Amazon. How many sensors do you need? Maybe 1.2.
In space.
That's not enough. No. You need to know, by camera,
Yes,
that's not enough. By that time, everything would be burnt. So you need to detect the changes in the temperature, and you need to have it like millions of sensors. Okay? Now, all that data coming from those sensors, if you're not going to process them somewhere nearby there, you're in trouble. So having some type of resources in place to do that, so we're talking about this type of system. You have like millions of these. So having those resources in place there based on the demand that you get, based on the information that you're getting, and optimizing on that. And if there is a fire starting, then you would know ahead of time and go and try to solve it, right? So that's the type of advancement that it is enabling. Okay, let's see. I'm going to skip this. Okay, one of the final things here is this is the Global Sustainability Initiative and the Climate Group. So this is the amount of carbon emissions that you have, and this is, as we said, growing, and you're trying to reduce the part out of the technologies that is using up that or generating that carbon into the environment by making the devices, by making the infrastructure smarter. Okay, so just the sheer, I need more data or I need more processing. Let me add a server. That's not the cure. Okay, because that is causing basically double the carbon emissions. If you don't need that, if you can do it in a more efficient way through cloud computing, why don't you go ahead and do that? Okay, so so smart infrastructures, there are lots of challenges, and we're going to the example of smart grids in a bit, and this afternoon. Some of the challenges are that the demand is an aggregate of several people. Okay, it's the aggregate of the behavior of a community of users, and the actions that you require sometimes require the collaboration between different people. So those are some of the big challenges. You also have several technology challenges. That's why we're going to go into two examples of the smart grids and then smart transportation. Okay, so before I go into smart grids, do you have, I'm going to start the video on smart grids now, hopefully to wake everyone up. So is there, do you have any questions about smart infrastructure and what makes an infrastructure or a device smart? Yeah.
Is there like an unlimited number of resources in the cloud? Or like
So we mentioned yesterday that you perceive an unlimited number of resources, but it's not an actual unlimited number of resources. As long as you're paying for it, it's there,
so
right?
what if everyone wants a lot and there's not enough?
Well, that is the problem. That's why you're trying to make your costs of the cloud even cheaper by reducing, let's say, the cooling costs by putting them in the North Pole, by putting them underground. So if usually with high demand, you can do this things at a massive scale and then reduce the price, and then you can build more, right? So that's one. The other element is as long as the demand is there, you can put more money into research and development, which would improve the technology, which would reduce the price. So you have that too. Yeah.
Is there any infrastructure element that you think you could not be effectively made as smart, like these infrastructure?
It depends on what intelligence you can get out of the data. Okay? Data as is when you collect it from sensors is data. When you process it, when you analyze it, when you come up with decisions, which is what you're going to do on Thursday, that is intelligence. Now, if that intelligence can lead to actions that improve the performance, then it's intelligent. Okay? If you're at the extreme of what is possibly done, and that data is not giving you an additional benefit, then you can't do too much about it. Like one possible infrastructure that can't be too optimized could be, I don't know if you can consider that as infrastructure, is this room. You can fit in it this many students, this many computers. Unless you make computers smaller, you can't fit in it more than this number of computers. If you add sensors on the entrances to try to do something better, you can't, right? But if you talk about, let's say, a bridge, and whether that bridge could be made more intelligent, yes, by adding better detectors to detect any faults that you might have, so that let's say you have an idea that a bridge is going to break down before it breaks down. If you have sensors that detect the flows on that bridge, and based on that you optimize the performance around it and other roads around it and things like that. So most devices you can add smartness into it by specifically adding sensors and finding the right technology that would help you solve a problem that is there. So the first thing is to find a problem, and hopefully in the future some of you could have startups solving some of those problems. Okay? So